Yeah, hello. So welcome to the presentations about Userspace Livepatching on PowerPC64. It will be performed by Giuliano Belinassi from the toolchain team. And if you have any question, then you could feel free to ask even during the presentation. Just please come to one of these microphones that are in the middle of the room. Yeah. So, Giuliano.
Okay, thank you. So I will present the Userspace Livepatching on PowerPC64, our quest to have it running on the IBM machine. But first, I will remind about what is Userspace Livepatching on x86-64, the Intel architecture. So it's basically is a way of redirect functions calls. So if you call a function that it has some bug, and you want it fixed without reloading the program, well, you load a new version of the function and call it instead. So any call that would go to the older version of the function now is redirected to the new version of the function. And it's very tight to the architecture because we need to, well, redirection, and every machine has its own way to redirect functions. So basically, this is mostly how it works. So on the left side of the slide here, we have the old function. So whatever calls it, there is a no operation product that does nothing when the function is not livepatched. And well, it executes the old function and it returns, so it proceeds to the normal operation. However, if we do livepatch this function, our no operation product gets replaced with a redirection to another product, which contains a full jump with a full 64-bit address of our new function that doesn't contain the bug or has its security problem fixed, or it's faster or whatever. And when it's done executing its task, it returns back to the caller, and the program continues normally. So that's how Userspace Livepatching works on x86-64. Yeah, so when we are preparing the library to be livepatchable, we actually use this flag here, the fpatchable functions entry. On the x86-64, we pass this 1640, which basically means I want 14 knobs before the function symbol and 2 knobs after the symbol, the function symbol, because on this 2 knobs after the function symbol, we will go use the jump to the larger prolog, which contains the full jump to the full 64-bit address. And that's how we redirect functions on Userspace Livepatching. This is just a figure just to show how the redirection is done. So what we do on the full redirection is we use this JMP0, the PC, the RAP, which is the program counter, and then we embed the instructions on the function address on the instructions there. So as you can see, GDB is showing garbage instructions because that's not an instruction, that is a function pointer. And if you execute this code, it will go straight away to our new function. And well, to apply the live patch, we actually have to hijack the execution. And we do that by using the ptrace system call, the ptrace setrex, which is wrapped around the OLP trigger command, which when you install a live patch, Zyper will eventually calls it. And what it do is to inject the Libpulp routines, so our management routines that are loaded together with the program, into the program counter register, which is x86 is the RAP register. and we continue with execution of the program with the process. So it's simple as that. And if by any means we want to skip the live patching function, so for example, we want to call the original function, either because we are appending some, let's say, well, I want to live patch this version function, so I want to get the old version plus some suffix. On x86-64 is as simple as adding 2 to the function pointer. So we can skip the 2 knots there, which, if live patched, will be a jump to our local prolog. So as I show you on x86-64, we abuse the fact that we can jump without using registers. And well, it's a CISC machine, so you have all sorts of complex instructions. But on powerpc64, it's a RISC machine, and every instruction has 4 bytes. So you can't have this kind of trickery to, well, jump whatever you want. And yeah, there is also the problem that on powerpc64, functions have 2 entry points. A global entry point and a local entry point. In the global entry point, you set up the table of content pointer, which basically a table that shows you how you can access global symbols, global variables, and such. And then it falls into the local entry point. So if you are live patching a function that only has local entry point, it should work as well as global entry point. And well, on PowerPC, we have the following ways to redirect. Well, we hold like comparing stuff, but we directly redirect to an address, which is the branch instruction, when you can pass an offset, which is a 24-bit constant. It's not fully 64-bit. Or you can branch using the link register, which is the BL instruction, or branch using the CTR register, which is the control register. So whatever we do, we have to save registers into the stack. There is no way around it, which is not pleasant, because on x86, we can just jump straight away at the function we want, and we are fine. And beginning with the project, we noticed that GCC was outputting some weird stuff. So on the left side here, this is what happens if we compile as like a very simple program that returns some global function, some global variable, with the fpatchable functions entry. So here we can see the global entry point. And now we go, here is the local entry point. And now we have a problem, because if we call the global entry point, we'll get into the prolog that we'll actually have to write. We want to write the full redirection code. So we'll have to, like, on every program, we'll have to post-process it and do some kind of jump here, which is not really great. So we actually had to patch GCC, some modified GCC, to make it right and output on the right side, which is before the function entry point. And we had all sorts of problems with that, but once it's fixed, we could move on. Okay, so we eventually got to the first version of our redirection code. And it's basically save a bunch of registers into stack and jump to the new function. So we set up the function address to R12, which is the global entry point register. We save the link register, which is used to redirect branch and call functions. We set up the stack pointer. We push the table of contents into the stack. We save everything. We jump to the new function. Then we restore everything, and then we return, and that works. However, as you can see, the arguments are passed through the stack, and it works most of the time, but there are some catch-ups here. For example, the first 8 parameters of a function on powerpc64 is passed through register. So if your function has up to 8 parameters, this approach will work. However, if it has more than 9 parameters, this will crash because the arguments are passed through the stack now, and whatever the new functions wants to read the value passed by the caller. Now we got garbage, and the program will crash. So we started looking. Okay, so how bad is it on glibc and OpenSSL, which is currently the libraries we currently support, and we found out that, well, it's small but not it's small but not we can't ignore that. So we started looking on how the kernel guys fix this problem, because kernel actually managed to do it correctly. So the way they do it is they create an extra stack, which is the kernel Livepatching stack, that grows on opposite direction from the thread stack. And well, okay, this works, but on Userspace, we can't find, well, there's no way we can find the end of the stack pointer. So we can't do this sort of approach. And well, the only way around it is that we allocate our stack on the heap itself per each thread. So not very interesting, but that's what we got. So, but we eventually developed the solution. So what will happen is that, on the prologue, we redirect to code running on Libpulp rather than jumping straight to our new function. And then, well, Libpulp then do the administration problems by itself. So it will allocate the ULP stack, save the LR and TOC registers, then redirect the function, and restore those registers, and return to the caller. So the program continues. And of course, we managed to actually free resources whenever the thread is destroyed. So we use the DP thread keys interface for that. And well, it doesn't leak in memory, which is excellent. But of course, it has a huge overhead, which we will see ahead. So we reduced the prologue size to 13 nops, which if you multiply by actually 14 nops, which if you multiply to 4, you have the number of bytes. And yeah, so we actually allocate a small piece of code we allocate a small piece of data on the thread local storage, which contains a pointer to our stack, but we can't actually allocate the entire stack on thread local storage. Otherwise, we will be we run out of thread local storage pretty quickly. We can't have that. So yeah, that's how we do it. And well, while writing code in assembly, we figure out that we can basically do this sort of construct to reference to a thread local storage, which is load through R13, which is the thread local storage pointer. However, this sort of construct actually generates a text relocation, which instructs the linker to actually go there and replace whatever is in this constant with another constant. But this happens after our program has been loaded. So this means modifying the text segments after the program is loaded, which means seccomp blocks it, and we have a system crash. So IBM guys wasn't happy with that because it made the system not bootable. So we had to fix it as well. And yeah, so eventually, how we fixed that? Well, we didn't use any sort of TLS optimizations. So we have to all go through the TLS get address function, which if anyone knows that, it do the same thing as getting the address of the TLS function, but it goes through glibc, which is extra overhead. Yeah. So sad, but works. So, well, about the execution hijack, it works very similar to how PowerPC64, on PowerPC64, the execution hijack works very similar to how on x86-64 works. So just had to modify some constants, which is the red zone. On Power ABI, it defines to be 1512 bytes. The kernel uses that for some other stuff. And we also have to set up the global entry point register, which is R12, to the function address, which is trivial. And yeah, the bitrace interface continues the same. It's all the same thing. However, for skipping the prologue, so for example, if you want to call the old function to get whatever version of the library it's running and then append a suffix for that, that's not as trivial. It's because we have to bypass that global entry point that we saw earlier. And we have to embed the TOC, the table of contents, preparation on the caller rather than the Kali. So in this image here, we can see whatever what I am talking about. So we have actually to bypass to after this B instruction, which is branch. And that means skipping the global entry point. So whatever we need to run here must be added on the Kali rather than the caller. So what we do is actually we go to the function read whatever this constant is and embed some more assembly code on the function that we want to call. And the Kali, and well, it works, but well, with some extra ugly code. And then we add 12 bytes, so we can go straight to the old functions code. And yeah, that works. However, for doing that, we need at least one register. So that if you want to call the old function, we can't have parameters on the stack and up to 7 parameters, which is fine for our use, and it's only used for testing and getting older versions, which on that end it's fine. So yeah. So what is the performance impact when compared to x86-64? When we compare the x86-64 Userspace Livepatching to the PowerPC64 Userspace Livepatching, well, just enabling the Userspace Livepatching, we can see that we don't have much impact. So we have, for example, up to 2% impact, when on x86-64 we have up to 4% impact, which is a good news. However, the per call, we have a huge overhead, so a 35% increase when compared to x86-64. And you can see that the call, the cost per call on x86-64 is much lower than the PowerPC64, which is interesting. So that's what we have. So in conclusion, what we can have, well, what we can conclude about PowerPC64 Userspace Livepatching. Well, it will be available for SLE 15 SP7. We have everything there already complete. It's able to live patch as many functions as wide as x86-64. We don't have any problems regarding limitations regarding number of parameters or if arguments go through the stack. However, we have a larger memory footprint because we have to allocate S-trace stack for each thread, and that could go on indefinitely until the program goes out of memory. If it's recursive, it's worst case scenario, but yeah. And of course, we have a 45% execution impact overhead per call, which is not great, but that's what we have it. So what we can do for improve it? we have to attack this overhead time. So what we are planning is actually try to analyze the function to find out whether or not we can skip the stack allocation, or simply perhaps jump ahead to the function by using that branch thing. And yeah, that's what we have it for now. Thank you. Any questions?
Maybe it's a comment and not a question. So you do actually, on the live patching action, patch the text section, right? Because
Yes.
you replace, so the text section has to be writable for all patchable programs, right?
No, it doesn't need to be writable. But what happens is that you can trick an external program to patch it for you. So that's the interesting thing. So an external program can do ptrace and modify the memory whatever you like, whatever the segment is writable or not. The kernel doesn't complain about that. So what we do is actually the patching is not done on the Libpulp side, but by an external program. So our OLP2 actually, so there is a communication between the target program and the OLP2, and whatever say, okay, I want you to write those bytes on those addresses, and the OLP2 actually go there and write it for you. So it bypasses whatever security there is there.
So any restriction you put on ptraceability would inhibit the live patching, for example.
Yeah. So if you somehow you say, well, ptrace can do that, then you can live patch, but then you can debug some other software. So it's very tight with the debugger as well. So whatever you do with ptrace, you either breaks GDB or Userspace Livepatching. Any more questions?
What about recursive functions? Is that second stack also growing like the other one?
Yeah. So if if you have a recursive function, there's no way around growing that stack. That's how it works. Because you have to push the other versions of the registers, and that's how it works. Any more questions? Okay, thank you.